Okay, Bismillahirrahmanirrahim. Okay, let's continue. So we are going to learn about the conduction phenomenon on composite wall. Yeah. Okay. So in previous video, we know that in common conduction, yeah, common conduction, we only have one kind of material. Yeah, so let's say this is a material, and then this is the A, which is the higher, and then this is the B point. Okay, so I will change not A but 1. Yeah, and then for the TP is the lower. Yeah, and then this is uh, the delta X. Yeah, so it's only have one kind of material. Okay, now, so what if we have composite wall? Yeah, so composite wall is consists of more than one kind of material. So let's say we have material number 1, and then material number 2. Yeah, so this is the higher point of the temperature, and then this is for the lower. Yeah, and then this is the delta x1, and then this is the delta x2. Yeah, this is material number 1, and then this is material number 2. Yeah, so it consists of two material. So it is called with composite wall. Yeah, or sometimes it also composite composite plan. Yeah. Okay, now how we deal with this situation. So firstly we have to know, yeah, a new variable called thermal resistance. Yeah, so thermal resistance is R. Yeah, so the symbol of thermal resistance is R. Yeah, so this is R delta X per K times the area of the material. Yeah, okay, and the unit, yeah, the unit of R is this is the unit of R as Kelvin per watt. Yeah, so this is the unit of R. Yeah, delta X per K times A. Yeah, and after so what is R? Yeah, so actually R is like the so okay, in this composite, yeah, we have, because we have two materials. Yeah, so it will have a lot of values of K. Yeah, the first one we have K1 and then K2, and if our material consists of 3, so we have K3. Yeah, so R is the um, alternative uh, alternative value, yeah, of K. Yeah, okay, so because we want to combine, yeah, we want to combine this material into one material. Yeah, because we have one material and then two material, and we want to make these two materials become one material. Then we change the K into the R. Yeah, because because after only after we got the value of r, then we can find the value of h. Yeah, so the value of h, yeah, will be the delta x. Yeah, so this the delta t. Yeah, so if we take a look on this picture, so this is the T1. Yeah, so this is T1, so I will make it bigger. And then on the other side, yeah, it is T3. And the delta x here, yeah, the delta x here is a different is a temperature difference, yeah, between the temperature on each side, yeah, which is T1, yeah, minus T3, yeah. And then the the delta t, yeah, so this is the delta t divided by R total, yeah, so this is the R total, yeah, because we have two material here, so actually this is the first K, yeah, so this is K1, and then this is K2, yeah, so K1, yeah, will be alternated with R1, and then the K2 is also alternated or change with R2. Okay, now for the ease of understanding, so I have example here. Okay, so the direction of the heat transfer, yeah, is from this point into this point, yeah, because you can see on the screen here there is an arrow that move from this point to this point, yeah. And I think this is logic, yeah, because the heat transfer will move from higher temperature, so this is the higher temperature, to the lower, yeah, temperature. So this is higher temperature. Okay, and we have three kind of material. The first one is called plasterboard. The K value or the thermal conductivity of plasterboard is 0.1 watt per watt divided by meter Kelvin, and the thickness of the plasterboard is 12 millimeter. And also we have second material, which is bulk, and the properties is like the property is as you can see on the screen here. And also the third material is bricks, yeah, and the K value and also the thickness as you can see on the screen, yeah. Okay, now what we are going to do is we find the value of every R, yeah, for every material, yeah. So okay, uh, but I think we have to change, yeah, the value of every properties here into the international unit, yeah. Okay, so for the first one we have the higher T, which is 22 degree of Celsius, so we have to change it into Kelvin, so 273 plus 22, so we have 295 Kelvin, yeah. And then for the lower temperature we have 4 degree of Celsius, so it will be 277 Kelvin. Yeah, so this is for the temperature if we convert it to international unit. Yeah, and then for the thickness. Yeah, the thickness of every material. So for the T1 we have 12 millimeter, so it will be 12 times 10 to the power of minus 3 meter. Yeah, okay, so this for the T2 and T3. For the second thickness, it is 150 millimeter, so it will be minus 2 meter. And then for the third material thickness, so it will be uh, okay, so for the thickness we have all value in international unit. Okay, now we find the R value. Yeah, we find the R value. So R1 is K1 times A1 divided by, oh, I'm sorry. Yeah, so the formula of R is the delta x1, yeah, divided by K1 times A1. Yeah, okay. So the delta x, or the thickness, yeah, so the thickness of the first material is 12 times 10 to the power of minus 3. Okay, so we have 12 times 10 to the power of minus 3 divided the first k. So the first k is 0.1. Yeah, 0.1 is 10 to the power of minus 1 time the area. So because the area of every port, yeah, of every layer is similar, yeah, are similar, then all the value of area will be 25 meters square. Yeah, so it will be 25. Okay. Okay, so I will use my calculator to find this value. So it is 12 times 10 to the power of minus 3, and then 10 to the power of minus 1 time 25. Okay, so I have 4.8 10 to the power of 3 Kelvin divided by watt. Yeah, okay, so let's see. The international unit of R is Kelvin per watt. Yeah, Kelvin per watt. And then we calculate for the second R. So this is the second R. So delta x2. Yeah, so our delta x2 is 15 times to the 10 to the power of 2 divided by k2 is 4.0, 4.0, yeah, time the a is 25. Okay, so I will use my calculator again, and I got 15 times, okay, then it is 0.4, yeah, times 25. So I got 0.015, yeah, Kelvin over watt. And then the third R, so for the third R it will be the third thickness is 8 times 10 to the power of 2, yeah. Okay, so it must be 2, yeah, because it is 18, yeah. Okay, so I will change this. And then K, the K is 0.7 A3, yeah. The A3 is 25. Okay, so this is 8 times 10 to the power of minus 2, 0.7 times 25. Okay, so I got 4.57 10 to the power of 3 Kelvin per watt. Okay, so we already get all the R, yeah. And then we are going to find, yeah, the value of the heat transfer. So this is the H, yeah. So the H is delta X, yeah, divided to our total, yeah. Okay, so the value of the heat transfer is delta X plus the our total, yeah. The delta X, not delta X but delta T, yeah. The delta T is okay, minus 277, yeah. And then the R total is you you sum all of this value, yeah. So you have 4.8, yeah, 10 to the power of 3 plus this value 0.015 plus 4.57 times 10 minus 3. Okay, so the result is so wait a minute, to minus 207, and then 4.8 times 10 to the power of minus 3 plus 0.015, 4.75 times 10 to the power of minus 3. Okay, so I got 771 watt, yeah. Okay, so this is the value of the heat transfer, yeah, from this point to this point through 3 layers of different material, yeah. Okay, now this is the application of conduction, yeah, the application of conductive concept in a composite wall. And after this we are going to learn about another kind of heat transfer, which is the convection. Okay, and thanks for your attention, and see you on the next video.